I'm going to talk to you about one of the simulations from Phet, Colorado, called Bending Light. There are 3 screens, but really the introductory screen is absolutely fine for what we need. This is showing air and water with a boundary. The normal has been drawn as that dotted line. We can remove the normal or add it in. That's always our reference point for any angles we're measuring. And I can either send a ray of light, so I click that red button to start the light coming out. I can change the angle of incidence, and as well as showing a ray, I can also show a wave. Let's concentrate on the ray first. So what I have is an incident wave or ray, a partially reflected ray. The angle of incidence between the incident ray and the normal is equal to the angle of reflection between the normal and the reflected ray. And this stays true for any angle that I use for my angle of incidence. And I can see my refracted ray, which is inside the water. In this case, it tells me that that's the name of the water. The name of the material is water. As I increase my angle of incidence, my angle of refraction increases, but my angle of refraction here is always smaller than my angle of incidence. I can measure my angles using this protractor, and you can see I have my 0 along the normal, and I'm measuring all my angles with reference to the normal. And you can see inside here as well, I've got 0 at the normal, and I'm measuring everything with reference to that. I can change the material. So at the moment I've got water. I can change to using glass, for example. And if I use glass, my refractive index is 1.5. And you can see that I've got a smaller angle of refraction. So nothing's happened with the reflected ray. It's the same for the angle of, same as the angle of incidence, whatever material we're looking at. But it's the refracted ray we're looking at here. If I use the wave simulation, you can see the wavelength, those wave fronts moving along. The wavelength is the same in the air as it is for the reflected, reflected and the incident waves. But if you look inside the material, you can see that that wavelength is smaller because the light is traveling more slowly. And if I go back to looking at water, which has a smaller refractive index, a refractive index closer to that of air, the wavelength is slightly longer. It's still less than the wavelength of in air, but it's smaller than the wavelength in, it's not as small as wavelength in glass. You can use slow motion. I'm not sure that's particularly helpful at this point. But this is just quite nice. You could get some actual quantitative pieces of information. If you were using the ray, you could measure some angles, 30, 40, 50, 60. Your students could maybe see if they can verify that, whether the simulation is accurate in their own experiment, or they could just use some data collection and plot a graph and see whether the relationship for Snell's law, sine of incident angle over sine of refracted angle is a constant, for example.